Good evening, Prof. Wang, and good morning and good evening, everyone. So it is my great pleasure to introduce our speaker today, Professor Wang from Stanford University. So the title of today's webinar is HyChem Modeling of Real Fuel Combustion Chemistry. Before we start the webinar, please allow me to introduce Professor Wang. Professor Wang is from Department of Mechanical Engineering at Stanford University. Before Stanford, he was the Northrop Chair in Engineering and Professor of Aerospace and Mechanical Engineering at USC. Professor Wang received his PhD in Field Science from Penn State in 1992. He was a professional research staff at Princeton University from 1994 to 1996, before starting his faculty career at the University of Delaware. Professor Wang is best known for his work on the mechanisms and models of PAH and soot formation in combustion and development of chemical kinetic models for fuel combustion. He has made contributions in the application of ab initio quantum chemistry and the reaction rate theory in chemical kinetics. He was involved in the early stage of GRI 3.0 mechanism development. He developed several widely used combustion reaction models from USC Mach2, JetSurf to HyChem. So HyChem is the topic of today's webinar. Professor Wang also developed the advanced stochastic methods for detailed modeling and uncertainty quantification. He contributed to the transport theories of nanoparticles and large molecules, atmospheric heterogeneous chemistry, nanomaterials synthesis, characterization, and applications in solar cells and lithium-ion batteries. Professor Wang was the recipient of the ARAA Propellant and Combustion Award in 2018 and the Humboldt Research Award in 2019. He is the fellow of ASME and inaugural fellow of the Combustion Institute. He currently serves as the editor-in-chief of Progress in Energy and Combustion Science. Professor Wang is the vice president and also the president-elect of the Combustion Institute. So Professor Wang, now I give the time to you. Thank you very much.
Thank you very much, Professor Song, and thank you for inviting me. I'm very excited to give this webinar. I don't reach this audience easily. So thank you for giving me this opportunity. And thank you all for joining the webinar. For most of you, it's 10 o'clock in the morning, so on a Saturday, and I appreciate that you come in, you drop in. And what I try to do is make this talk as light as possible. I try not to bore you with too much technical content. The key point I want to make today is that as far as the combustion chemistry work is concerned, our community is overthinking about this problem. There are simpler ways to handle the problem and leading to much smaller reaction models that you can implement in your OpenFOAM code and thereby facilitating and speeding up the development, especially for real fuel combustion chemistry problem. All right, so let me just go on first to thank people that I work with. Along the work of HyChem, the person that one of my students that worked on this most extensively is Ray Xu. He is currently in SLAC, the Stanford Linear Acceleration Laboratory, and also Kiara Sargis, who is now at the Lawrence Livermore National Lab. And all of the data of this work comes from my colleague, Ron Hansen, Tom Bowman at Stanford, and Fokian Igofopoulos at USC, Ken Brzezinski at UIC, and the model reduction was all done by Tianfeng Lu. So I think that Professor Zhang already introduced me, so let me just give you a flavor of perhaps from my career point of view, where this idea of a simplification for chemistry come from. Okay, I was trained as a physical chemist, as Professor Zhang indicated earlier. I worked on a very wide range of combustion chemistry models. Some of them are more known than others. GIMAC came out actually from the approach came out from a chapter of my PhD thesis that extended into a multi-university collaboration that led to GIMAC 1.1 and 2, and eventually 3. USC Mac 2 is not as popular as many mechanisms out there. For example, compared to Galway mechanism, it's less popular, but it's been used quite extensively. JetSurf was the earlier version of a HyChem, so to speak, but follow a detailed reaction chemistry method. HyChem is what we want to talk about, and the other line of work that I do is PhD sort chemistry. My current research interest is somewhat away from chemistry, more in gas dynamics, in detonation, but with quite a bit of propulsion combustion chemistry. We work on certain materials issues involving phonons and transient pi binding, and we continue to work on a range of battery problems. More recently is alkali sulfur batteries. Okay. Now, since I don't have opportunities, I'll take this opportunity to say that speaking about detonation, we have actually several positions, postdoc positions in the area of reactive flow modeling. This I would say between chemistry and gas dynamics, fluid mechanics, they are fairly evenly distributed. And we have several positions. And OpenFOAM experience is in fact desirable. If you're interested, please contact me by email, it's listed here, Wang@stanford.edu. Okay, so let me get into the technical content of today's talk. Now, this is a chart in a paper, a PAX paper published by Professor C.K. Law and Professor Tianfeng Lu a few years back. It is a chart that lists popular reaction mechanisms or reaction models, which, by the way, I forgot to say one thing. I sometimes use the word reaction mechanism. Sometimes I use the word reaction models. The more preferred way of calling this type of work is we do reaction model development. Mechanism is a very strong word. Mechanism is how nature works, and we can only mimic how nature works. So everything we do is a model. It is not exactly how nature works, and we try to mimic that. So now, as far as this chart is concerned, it lists some of the popular mechanisms. For example, the large range of Lawrence Livermore National Lab mechanism, some of our model, JetSurf, USC Map2, and so on. Okay. What this chart is trying to show is how does the number of reactions depend on number of species. But I wanted to key point I want to draw your attention to is that some of those reaction mechanisms have reached to roughly, yes.
We are still stay on the first slides.
Oh, okay, that's strange.
Oh yeah, no, it's okay. Yeah.
Somehow the okay.
Yeah, no,
right.
okay. Yeah.
This is okay, yeah.
Yeah.
Does it show the full screen? For some reason,
not full screen.
It's not full screen.
Not full screen.
How is it now?
Still not full screen, but we can see the slides of speaking about detonation.
Oh, how about this page? Which is interesting. Somehow my full screen show does not.
Just now, you show the first screen. Just now.
let me just do this. And let me stop and reshare. Maybe that's what happened.
Yeah.
How is it now? What do you see?
No show yet.
It doesn't show, huh?
Has started a screen sharing, so we need to wait for several seconds.
Huh. This is very strange. Let me try this again.
Okay, no problem.
Anything?
It shows has started a screen sharing, so we need to wait for a couple of seconds. Should be okay. Yeah, should be okay. We wait for a while.
Shouldn't take that long. Oh, it says my screen share is paused. And how do I unpause it? This is new to me.
So you click the button. Oh, no, yeah, it's okay. Yeah,
Now it's okay.
Yeah, full screen. Yeah.
Okay, wonderful. It's a full screen, right?
Yeah, correct.
Okay, wonderful. Yeah.
No problem.
Yeah. Okay. So this is just a job ad. It's posted on the symposium website, and if you're interested in postdoc position, please check this out and contact me by email. All right. So now let me unwind a little. Talk about this chart. Okay. First of all, we talk about reaction models. I don't like to call them reaction mechanisms because mechanism is a very strong word. So that's one thing. Second thing is this is a chart from Professor C.K. Law and Kim-Feng Liu's PAX paper some years ago. This is some popular reaction mechanisms from Lawrence Livermore, CNIS, to some of the USC mechanism to early days GI Mac. Now, the key point I wanted to draw your attention to is today, modern day reaction models have reached something of 10,000 chemical species. Now, many of you work on in the area of OpenFOAM and the fluid dynamics or combustion, turbulent combustion modeling, all gonna wonder how would this model ever gonna be used in your simulation? The idea over the past decade or 2 decades or so in the combustion community is you develop detailed mechanism, many species, many reactions. You then try to reduce them to a smaller set. Hopefully, it will fit into your CFD simulation. Can we do even better than that? Do we really need that many chemical species or chemical reactions to describe a fuel combustion? This is the question I want to address today. Now, the other issue that we're facing in this community is that, first of all, if you ask me how those reaction mechanisms were compiled, tested, and published, typically we do a critical review of literature kinetic data. Now, because you reached something of the order of 100,000 chemical reactions, your reaction rate parameters are not all well known. As a matter of fact, for those reaction mechanisms, 99% of rate parameters are guessed. Guess might be not a so nice word. I would say that those are estimated based on analogous reactions, so they are empirical. And you compile a model, you would tune some rate parameters against a set of experimental data. Then we use this big word called validation. That is, do lines as predicted by the model go through a certain set of data, and from there we will publish the model. Because there are many hydrocarbons that we have to consider, this have led to many models. Okay, so there's a many large combustion reaction model problem, and for a user, you often are left with the question of which model you should choose to use. And I found this from CFD community the tendency is always you have a bias to use a smaller model. And I want to tell you that this is actually the right way of doing it. And I will make this point shortly. So the state of the knowledge is many models, we also have very large uncertainties. And many of you compared, say 3 or 4 reaction models have all seen this problem. Okay. Now, then talk about real fuel. What real fuel are we talking about? I'm talking about gasoline. I'm talking about jet fuel. I'm talking about a multi-component liquid fuel. It's a soup of many components. It's impossible for us to describe the composition of this fuel exactly. We don't even know the composition exactly. You go to a gasoline pump, you get out a tank of fuel, and from season to season, city to city, place to place, this composition is not fixed. In fact, it varies with respect to where you get the original petroleum and which distillation column you used and what pipeline you have put this gasoline into and thereby transported to distribution center and so on. Okay. So historically, our reaction chemistry community takes a surrogate approach. The way how it is done is you use a mixture of neat hydrocarbons, around 5 or 6 of them, to mimic the real fuel behavior. And those are characteristically detailed reaction mechanisms or detailed reaction models. And you can size and reduce them for CFD simulation. This approach has many drawbacks. I was involved in the development of those large reaction mechanisms, and over the years, I started to wonder about 10 years ago whether this is the right way to do that. The first problem that I was bothered by was, how do I know, as large as those reaction models are they complete? And moreover, there's no way of assessing whether they're complete. And since I have, say, 1,000 reactions, just take a smaller reaction model. If I have 1,000 reactions, I will have 1,000 rate parameters. And as I pointed out earlier, you're going to get a majority of the rate constants that are guessed based on some fundamental knowledge. Yet, many of this rate constant cannot be directly measured. And as a result of it, they have a large uncertainty. With this uncertainty, you often wonder when you get a disagreement with, say, laminar flame speed measured, the discrepancy comes from model completeness or coming from uncertainties in the rate parameters. Okay. So these are the top 2 problems. Okay. Then, if you want to have a reaction model for real fuel, gasoline, jet fuel, you develop a surrogate. And a surrogate formulation is entirely empirical. So how good is it? If we assume those reaction models, because they are detailed and they are fundamental, when you apply them, you have to apply them empirically. Okay. So there are other issues. Surrogate model cannot account for both chemical and physical properties at the same time, just because real fuel, if you do spray combustion, you're going to worry about distillation curve. You're going to worry about droplets. And a surrogate or 4-5 component cannot reproduce these physical properties, viscosity, and so on. So in that regard, some 10 years ago, I realized that we need a new approach if we're ever going to make real impact on combustion simulation of real fuels. And that is also inspired by things that Albert Einstein said a long time ago, that with regard to the way how we understand nature, if you have a theory, or for that matter, if you have a model, you wanted to think of it in a way that everything should be made as simple as possible, but not simpler. In that regard, coming back to my earlier point, a smaller model that can describe a prescribed set of experiments is always better than a large model. Okay. So in that spirit, I wanted to start with a more detailed discussion about what is HyChem, where it's coming from, what are the fundamental bases, and in doing so, justify why it should be done this way, and in fact, it's a simpler way. So let me first just start it off by describing some examples of real field. Okay, the top three are jet field, Jet A, JP8, JP5, and they are more or less the same thing. They are just having different additives, and maybe some is sootier than the other. Nevertheless, if you look at this field A, they are multi-component. Multi-component comprising of paraffin, isoparaffin, monocycloparaffin, dicycloparaffin, and some aromatic compounds. Now, for jet fuel, the average formula is roughly around C11H22. If you look at the gasoline without ethanol addition, will be around C8. And if you go to diesel, it would be around C16. Okay. And then also, if you look at the fuels that are rocket fuels, they are isoparaffin, N-paraffin, and so on. Similar composition, except with distribution of the classes of compounds being somewhat different. Now, they do differ in composition. Yet, if you put JP8 into commercial airliners as a Jet A, it burns just equally good. Okay. So the thing that we should look at this whole thing is, with this complexity, the first notion we get is because of multi-component mixture, they must be more complex or more difficult to predict their combustion property. And that turns out to be not true, and I'll explain. Okay. Let me summarize. What is a multi-component real fuel? And I use aviation jet fuel as an example. It's a multi-component with a range of boiling points. Okay. So a useful chemistry model must allow for appropriate spray and evaporation modeling. That means we probably should just directly experiment and develop a model for the real fuel, multi-component or not. Composition is not exactly known. It can vary widely among different fuel grades. They can vary from batch to batch, season to season, region to region within a grade. But then, while knowing only a few chemical properties is enough to know this fuel is going to work well in an engine. So what I gave you here, the chart below, is what we call American ASTM standard. From application point of view, if you are an airline engineer, what are you looking for in this jet fuel to decide that this fuel is going to fly your airplane and your airplane will not fall off the sky? This is determined by ASTM standard. As a matter of fact, if you look at this ASTM standard, it's very simple. The first four properties are physical properties. That's density, flash point, and so on. The real chemistry property relate to the fuel. There are only three: aromatics, content, seating number, and hydrogen content. As a matter of fact, aromatic content is not critical. The reason you need aromatics in a jet fuel is because you need it to swell the gasket. Without aromatics, your aircraft will leak fuel. Okay. So the key number to look at is seating the hydrogen content. In fact, the specification itself does not say anything about the composition. So why is it? Let me explain. If you take a range of jet fuel, A1, A2, A3 are three representative jet fuels you found in the United States. R4, R5 are two rocket fuels. K6, 7, 8 are some other generic kerosene fuel. D is diesel. G is gasoline. Those are random samples you can find in, well, laboratories and in the world. And this set of ignition delay data are measured by Ron Hansen's group by David Davison. What you notice is that under a comparable condition, the ignition delay time of a real fuel all clustered around a very small band. In other words, when you get to a real fuel, the ignition delay time is not dependent on what fuel it is, and therefore their composition. What about the flame speed? This is a set of data collected by Folk and Ecofopoulos at the USC. So between JP8, the 3 different jet fuel, and also a rocket fuel called JP10, you find that they all cluster around a range not larger than 5 centimeters per second, whereas the error bar in the measurement is in fact larger than the variation of the flame speed you measure among these fuels. So now that's interesting. If real multi-component fuels are more complex in terms of this combustion property to predict, why do they all exhibit the same basic combustion properties? This is a question we have to address first, okay? So in summary, hydrocarbon types and composition exhibit only weak to no impact on high temperature combustion properties, and therefore is a fuel composition as a starting point consistent with underlying physics is the question we will start to ask when we started with this HyChem related work. So let me explain. Why is multi-component fuel mixtures is more predictable than a single component fuel hydrocarbon combustion chemistry? And to illustrate this point, I wanted to show you a set of Monte Carlo simulation that we did. It's a computational work. So we go to our computational cabinet, bring out some alkene, branched isoalkene, highly branched alkene, cycloalkene, and aromatics. So this is just like my numerical fuel cabinet. We have reaction models for them individually, and we have run large reaction models for it, and those are their properties, okay? The next thing that I wanted to do is randomly pick those chemicals out of my cabinet and randomly mix them, all right? And I wanted to look at how do combustion properties computed vary as a function of this samples that we take, okay? First thing first, all right? If I take 4 components, n equal to 4, that is, I randomly pick up 4 components and randomly assign their composition or concentration in a 4-component field. I will go get a laminar flame speed distribution that look like this with a mean around the 58 and a standard deviation, 1 standard deviation about, interesting enough, 4 centimeters per second, 2 centimeters per second, okay? And that, in fact, in many cases is equal to about the same as where you can do measurements using, for example, counterflow. All right. If I choose a 12-component mixture, again, take 12 components randomly and prescribe them randomly. In other words, I've been just behave like a terrible chemist, okay? Dumping components of the fuel in a single component into a mixture, and I shall measure then the flame speed. When you have 12 components, in fact, the mean is still around the 57, 58, but the standard deviation now is of the order of 1 centimeter per second now. Now you know where I'm getting to. If I have 18 components, all 18 being chosen, although concentration of each of the component being random, I'll get such a narrow flame speed distribution with a mean at 57 and a standard deviation is certainly smaller than 1 centimeter per second. So you trust me. Those of you who have measured the flame speed, and when I go talk to Professor Folk and Ecofopoulos, Professor Ed Law, they will assure me that they will not be able to measure the flame speed to that accuracy. Okay, in other words, what I show on top is a cluster of data under the conditions shown for jet fuel and for rocket fuel. What you can see is that symbol correspond to the flame speed under that condition, and error bar represent the measurement uncertainty. So what I'm seeing here is something that's very simple. When you get to multi-component mixture, and as long as you have sufficient number of components in this mixture, they all gonna behave the same combustion. Now, then conditions. And we'll do statistics on them. Laminar flame speed of few components, again, randomly selected between 2 components, 4 components, all the way to 18 components. What you see here is, this is again the Monte Carlo sampling. The solid line is dashed line deviation. Other lines, you see here to about 12 components, for example, your 2 standard deviation in flame speed have dropped in a second. And this is roughly how accurate speed. So if you were to do flame speed measurements, and the fuel composition or mixture you have, you're roughly going to get the same flame speed within the experimental measurement uncertainty. For lean, stoichiometric, and rich mixture. What happens to ignition delay time? Same thing. You look at 12 component mixture under a set of conditions. Typically, my colleague Ron Hansen can do measurements in his shock tube. And Ron can do ignition delay measurements with about a 20% uncertainty. And that uncertainty in the measurement is equivalent to subscribing or prescribing, a mixture of a 12 component field with arbitrary composition. His shock tube won't be able to tell the difference. For extinction resonance, the difference becomes negligible. So in summary, multi-component mixture are more predictable in terms of combustion property than single component. For with a single, before you multi-component is an incorrect notion, in fact. Okay, and this have graduate students or postdoc who will become a professor. The secret for all of us is not so. The mean is always the same. Roughly know the same. And therefore, the year will always use the same lecture notes. Okay. Now, let's say you wanted to teach each individual student in this 100 student class. Now that becomes a really difficult problem. You have to know the students a little bit more, each of them somewhat, in order to teach effectively. Combustion chemistry is far. I was a student before I'm going to teach a class of 100 students, and that for those of us who've been professors to go about it. For that, there's no way of even doing that in an effective way. All right. So far, everything I've talked about is about explore with you something of a flame. What does flame do when you not multi, but big hydrogen here? As an example, what I'm plotting here is the structure of an adiabatic flame. Let me explain slowly, okay? I have the temperature profile, I have the cold boundary, and this is a adiabatic flame. What you see here is the field I have seen. This is you form. You look at the structure of this flame, you find that where flame is intense as marked by chemiluminescence of electronic excited CH. This is where the blue flame is. It's somewhere here. Your temperature is already very close to the adiabatic flame temperature, the final flame temperature. But look at this. This large field, NB2 cyclohexene, is long gone, finished, disappeared, before the flow reaches the flame. So where did the fuel go? It went to ethylene, it went to hydrogen, it went to methane, and it went to propane. Now this is not new. If you go back to look at the Norbert Peters paper back in the 1990s, this is all being told in the context of how do you even determine the Lewis number for this type of flame. Nevertheless, So what will happen is that in this temperature region, before the flame, temperatures around 12 to 1400 Kelvin, the fuel already undergo pyrolysis. It's disappearing on you. Replaced by what? Replaced by ethylene, methane, propane, hydrogen, and some other minor species. Okay. And if I replace N-butylcyclohexane by other large hydrocarbon compounds, whatever this may be, they also crack. They may crack to different type of products, but they always dissociate. And as a matter of fact, if you have the feed fuse with that larger molecular weight into the flame, I can assure you this flame from fundamental flame dynamics point of view, the flame will never be stable because you run thermal diffusive instability there. So nature actually did us a greater favor there. That is, it doesn't matter what you burn, large hydrocarbon, they will dissociate into a bunch of intermediates that have similar molecular weight as a molecular oxygen. And that's why you don't run into thermal diffusive instability problem. Okay, so to summarize and quantify, for flames, you get this 100 microsecond window over temperature range of around 1050 to 1450 Kelvin. And this is when the fuel you feed into the flame got converted entirely to small hydrocarbon species. They decompose to a set of small species, and this is how flame works. This is one set of data. I always use it because it's a beautiful set of data, again, done by my colleague Ron Hansen. Okay. If you look at the mole fraction of species, shock tube oxidation of N-dotted king, C12H26, in oxygen, diluted in argon with equivalence ratio of unity. Okay, so this is diluted mixture, and so you can follow the species well. If you're interested in a legacy combustion property, ignition, that's about 700 microsecond. And within this 700 microsecond, you look at this problem, you say, fuel is gone in the first 20 microsecond, 95% of fuel is gone. Because keeping in mind, this is log scale, the time axis. Replaced by what did fuel? Ethylene. You see that? Ethylene goes up very quickly, levels off. And for the next 700 microsecond, you're doing not the oxidation of the fuel, but you're doing oxidation of the fuel pyrolytic product. Already, but never burn large fuel directly or never oxidize large fuel directly. You oxidize the fragments of its dissociation product. So that's the key point. How general is this observation? So summarize, we'll have pyrolysis first, oxidation second. Oxidation takes much longer, and they are, of course, rate limiting. That's a key characteristics of burning large hydrocarbon real fuel components. Okay, oxidation process takes 700 microseconds, and oxidation of ethylene is rate limiting. How general is it? And this is a set of data published some years ago by Ken Brzezinski from UIC. Rather than plotting the mole fraction of species in a time domain, Ken fixed the time of reaction to about 2 milliseconds in the shock tube. Then look at concentration of the fuel, which is here, he used N-decane, and oxygen as a function of temperature. And different symbols here represent different equivalence ratio, from fuel lean, stoichiometric, fuel rich, to pure pyrolysis, where equivalence ratio is infinity. Let me break this chart down. If I draw a line here around the 1200 Kelvin, did you notice? N-dotted king is all gone by 1200 Kelvin. Not much oxygen has been consumed. So where did N-dotted king go? It can only go to pyrolytic product. In other words, whether you do pyrolysis or oxidation, fuel always decompose first. And notice that at a different equivalence ratio from lean to pure pyrolysis condition with infinite equivalence ratio, you do not see variation in those symbols in the mole fraction of the fuel. In other words, the presence of oxygen almost do not ever impact the pyrolysis condition. And that's great. If that is the reason that we can start to decouple the process of fuel pyrolysis from subsequent oxidation of pyrolytic product by molecular oxygen. Okay, so those are the physics again, indicating measurement is fuel pyrolysis first, fragment oxidation next, and fuel pyrolysis is not affected by oxygen concentration. Why is it? Look at the pyrolysis, and this is entirely thermodynamic driven. So this is a complicated chart, and I wanted to jump in this for 1 minute. Bear with me. If I look at a Gibbs free energy of reaction starting with a fuel, I just generically call it C11H22. I have some enthalpy of formation, therefore enthalpy of combustion defined for this fuel. I ask that if I expose this fuel to 1300 Kelvin, 10 bar pressure, thermodynamically, as far as chemical equilibrium is concerned, what would it evolve to? Well, if I run this pyrolysis using, say, Pantera equilibrium code, what you're going to find is the final product of the pyrolytic reaction is actually carbon and hydrogen. If you will, this will be soot and hydrogen. All right. And what is the driving force? Enthalpy-wise, you see enthalpy continue to increase. That is, this reaction is endothermic. You need heat in order to get it going. The other way to look at this is, because of this endothermicity under adiabatic condition, the more you dissociate the fuel, the lower the temperature, therefore the slower the kinetics is going to be. So enthalpy is not a driving force. Enthalpy works against dissociating the product. What drives this process is, in fact, entropy. Entropy goes larger as you break down a hydrocarbon fuel into smaller components, mostly involving hydrogen. Hydrogen wants to go free, and this is why fuel likes to crack itself. And keep in mind, entropy goes up, and if I plot negative temperature times entropy, this should go down. You sum up enthalpy and entropy term, you get a Gibbs free energy. And it is because of entropy process driving the reaction with always negative Gibbs free energy to go to final equilibrium product. Yet because enthalpy is working against you kinetically, the system gets stuck somewhere here. Somewhere here is where you find dissociation products that you see in previous charts. Those are involving hydrogen, methane, ethylene, some C3, C4 species. So this is the thermodynamics of this problem. Okay. And thermodynamics of this problem is such, it doesn't matter what you start, thermodynamics will clean things up for you, leading to only a smaller number of components you shall consider or you need to consider. So if you start with 1,000 components, upon this thermodynamic filtering, you get only a few small species, and there's a small C1 to C4 species. That's the key point. And to prove this point, system always gets stuck in C1 to C4 hydrocarbons. I'll take N.ecking. I pyrolyze it at 1400 Kelvin adiabatically at a 1 bar pressure. Because of endothermicity of dissociation, the temperature drop as N.ecking concentration drop, replaced by ethylene, predominant, hydrogen, propane, 1-butene, some ethane, methane, and so on. Keeping in mind, this is log axis. So if you just consider this group of pyrolytic product, you'll find you're recovering 98, 99% of carbon mass. So again, the point is, pyrolytic products are trapped first in the local metastable potential energy basin, and they are stuck there, and for 500 microseconds, they do not kinetically dissociating all the way to hydrogen plus solid carbon. And this is the soup, in fact, we burn. And the time scale for this to happen is about 100 microseconds. Recall that in the flame, I talk about this 100 microsecond time scale. Okay. All right, so I'm going to jump through this. It's not important. So given all this understanding, what do we do? I want to make sure that I don't run too long. Don't want to take too much of your time for a Saturday morning.
It is okay. Please go ahead.
I'm sorry?
It's okay. Please go ahead.
Okay, all right. Thank you. So to summarize everything that I said, what are we seeing here? All the evidence, thermodynamic, chemical kinetic, statistical, and so on, all indicating that if I have a large hydrocarbon field, whether there's a single component or multi-component real field, I call this field generically a C sub M, H sub N. Under certain temperature, radical presence, and molecular oxygen presence. The initial reaction process, if you heat it, whether it's in the flame front or through other means of heat transfer, raising the temperature, what you're going to get out is a set of intermediates. I denote this intermediates as X sub I. Okay. And this process is fast, very fast. They're not really limiting. And it's not even dependent on oxygen concentration. And doesn't even depend on whether you are in an oxidative condition or in a pyrolytic condition. Then these intermediates or pyrolytic products, this is C1 to C4 intermediates, ethylene and so on, their oxidation in molecular oxygen finally producing combustion product. That's rate limiting, that's slow. So if you look at this physical understanding, how would I put a model together? I would jump through all of the large set of reactions describing how few get to those intermediates, okay? And it's unimportant how long it takes, because you remember for this shock tube problem I said earlier, ignition delay time is 700 microseconds, dissociation time of the field is 20 microseconds. If I'm way off, I'm off by a factor of 2 in field pyrolytic rate, rather than 20 microseconds of dissociation time, if it's 10 microseconds, your total error in the overall ignition delay time prediction is simply a few percent, okay? So the point here is, this first part, you can simplify it. The second part, you have to treat it very carefully. What it translates into is the following. Again, before I get to the next point, so far everything I talk about is theory and some limited experiments. So let me now give you some real field measurements to show that this assumption is valid and is correct. My colleague Tom Bowman did a field pyrolysis, field oxidation experiment, in his turbulent flow reactor. The reaction time is a little longer because we need to lower the temperature to see the species well. 20 milliseconds, 1 bar, 1140 Kelvin with 300 ppm of fuel. And what you find is that for 3 different jet fuels of different composition, the intermediate species that are produced from the initial fuel decomposition stay more or less the same, dominated by ethylene, some methane, propane, benzene, toluene, butadiene, ethylene, acetylene, and there's about half a dozen, 6 to 8. The rest you add together is relatively small, and this relative as far as the combustion goes doesn't contribute to heat release. You can simply put the rest back into the field if you want to model it. Right. The point is that all of this field have over 1,000 fuel components, cover 4 or 5 different organic hydrocarbon classes. But once you parallelize it through this first step, as if a pyrolytic process is a lens, you're actually focusing the reaction process down to production of a very few components, about 6 to 8 you in fact need to consider. And that simplification is also the necessary and sufficient condition for real liquid fuels don't vary in their combustion property, as I discussed earlier. And let's also explain why this is so. If all what I said is true, and you believe what I say, then we just needed to develop some very simplified reaction models. Taking the fuel called a CmH sub n. This can be a jet fuel, this can be a gasoline fuel. And all what you have to do is conserve mass, carbon and hydrogen mass. And you can massage the lump the reaction process into something that looks like what I'm showing here. All the Greek letters marked in red are properties, are parameter values that we need to determine. Where the blue letter, English letter, ED and BD, EA, and so on, are dependent variables. These values depend on the Greek letters, the alpha, the beta, the lambda, the chi, and so on. So if you ask me, why did I cast the model in this way? Is because algebraically it's the simplest, and each of these Greek letters are independent variables, and they have physical significance. For example, the parameter alpha is the number of H atom produced in the CC fission reaction per fuel molecule. And beta has its meaning. Gamma is the ratio of methane to, the methane yield per fuel molecule, okay? And this is in addition to H abstraction by methyl. Lambda 3, lambda 4, those lambda parameters are the ratio of higher alkenes, propane, and butene. This butene can be 1 butene, can be 2 butene, can be isobutene, and you can expand to it. Their ratio to ethylene. Ethylene is always one of the dominant products. Chi is the ratio of benzene to benzene plus toluene, and their range is bound, and so that you can only choose values between the value given by the blockage. The dependent variable ED, EA, and so on can be determined essentially from the fuel stoichiometric coefficient, C, M, and N, plus the various Greek letters. So the way how you cast this model is nothing more but to A, to make your algebra simple, B, those properties of stoichiometric coefficient values, in fact, can be determined by the experiment. And I'll illustrate that. So all this is done. You have to describe this intermediates. As I discussed earlier, there's a way to write simple algebra conserving the mass. And there's a hydrogen for the intermediates and ethylene and so on, okay? And one of the things we don't recognize when we write detailed reaction mechanism is a majority of those reactions you see in 100,000 reaction mechanisms do nothing but try to conserve mass. So in other words, if the reactions are not really limiting, what you write the reactions are for is only for conserving elements and conserving mass. So in a way, one way to say this is you're using integration to implicitly conserve mass. But since your carbon to hydrogen ratio in the field, if that is known, carbon to hydrogen ratio is known. In fact, your dissociation products must be correlated to each other. For example, if you look at the ethylene yield per any kind of fuel molecule called C11H22, plot against the methane yield, they are highly correlated, okay? And those are the few bands that depends on benzene toluene ratio. And you can show this, those bands constrain methane yield and ethylene yield very tightly, in fact. And those are some measurements down in Wang's shock tube for several different fuels. And also, if you look at the aromatic yield, they are also bound, very bound. There is a very small parameter space or variable space you can choose those stoichiometric coefficients. All right, all that said, how did we do this? Real fuel, pyrolytic process, producing those intermediates. This is a one-step lump the reaction model. It's anchored on elemental conservation and kinetic parameters, including those stoichiometric parameters, alpha, beta, gamma, will have to be derived from experiments. Once you have these pyrolytic products, their reactions are rate limiting, and you need to now switch to detailed model. And this detailed model can be reduced to about 30 species. And for that reason, the final HyChem model is about 30 species for a real field. You never need to have anything more than that. So we use experimentally measured species profile to inverse the problem, determine the kinetic model parameter. And those are what I showed you earlier. We have 6 stoichiometric coefficients. And for radicals of H, methyl O, OH, O2, HO2, 6 of them plus 1 more. So we have a 7 rate constant, 6 stoichiometric coefficients to determine from experiments. Okay. We do not use flame data or global combustion properties to fix those parameters. We only use measured species concentration to determine the model parameter. Then we test and validate the resulting model against the global combustion properties, flames, and shock tube. All right. So the problem is casted essentially into 13 independent variables that are to be determined by fundamental experiments. Okay. And we use a foundation field chemistry model. We use CMAP2, but you can use anything, as a matter of fact. It's not that important. And I'll skip through this to show that some of you might ask, how do I know those coefficients, the stoichiometric coefficients, are constants, independent of temperature and pressure? So therefore, the model as written as a constants, they are general. And we have a detailed arguments given here through very simple steady state analysis. And I will not go through, I'll jump through that. For those who are interested in this problem, you can read some of those papers, which I'll give you the list at the end. The key point is by throwing away perhaps thousands of reactions, just to write it simply, I have, for example, N dot king dissociated into hydrogen, methyl, ethylene, and so on. And each of these values is basically what I showed you earlier, related to alpha, beta, gamma, the Greeks. And then you have a second reaction, just with all being a series of radicals, and with their stoichiometric coefficients simply derived from detailed model. Okay, but now from few all the way to the small species are described by essentially 2 lumped reaction steps. You can reproduce flame speed extremely well, and you can reproduce ignition delay time without tuning anything. All right, so that shows that many of these detailed models are so many reactions are completely unnecessary. They are doing nothing more but to conserve mass, okay, through a long list of chemical reactions. So we do speciation from flow reactor and shock tube to develop a model. We then use global combustion properties to test the model. What kind of data? My colleague Ron Hansen measures the ethylene and methane species concentration as a function of time over a range of conditions. In this case, would it be for different fuels and a similar temperature pressure condition? And this is the kind of a curve we fit. By fitting this curve, we can back out those parameters, the HyChem kinetic model parameters. Those are the Greek letter parameters and rate constants. And you can do this over a wide range of temperature for yield of methane and ethylene and over different reaction time. Okay, it is this type of measurements we do. And you can also do this in oxidative condition. The experiments I showed you earlier are simple pyrolytic experiment. And you can do this in the oxidation experiment. Remember, with or without oxygen, stoichiometric or infinite equivalence ratio or pyrolytic condition, you don't see that much effect in species that are produced. And this is yield of ethylene again, and not much difference. Okay, so the lines are the model and symbols are experiment. The other type of experiment we rely on, okay, is the flow reactor. We can map out more species, but stretch the reaction over a longer period by employing lower temperature. So there's a constant temperature flow reactor experiment. This is the field for JP8, ethylene, hydrogen, propane, and 1-butene. It is a propane and a 1-butene measurement allow us to determine the ratio of this species, their yield to ethylene. Those are the lambda properties, if you recall. We have benzene and toluene. So the inverse of this problem is it allows us to fully determine those rate kinetic model, HyChem model parameters. And there are some more examples showing the measurements in shock tube and here open symbol model prediction. Okay. Now we have HyChem model. Trust me, 13 parameters, a lot to fit. So we need to have a quite wide range of experiments, but those are not too bad. Typically, for a given field, 2 weeks of experiments are good enough. And then you have all the model parameter with the HyChem formulation. The next question is, do some shock tube ignition, validate it. Turns out that most of the species measurements were made at 12 bar. You're then actually going to ask the question, can the model be extrapolated to higher pressure and to wider temperature range? The answer is definitely yes. Remember, those Greek letter parameters are not dependent on temperature, not dependent on pressure either. So as we expect, when you derive the model parameter at around 12 bar, apply this to 50 and 30 bar higher pressure, you actually predict things very well. And now when you get to the last set of experiment, you see you have a solid line and a dashed line. Symbols are experiment. The reason you have 2 lines is because when you get to that condition, air-like condition, you start to see NTC behavior. So once we add NTC chemistry, I'll talk briefly later, you reproduce the data much better. Long story short, wide range of multi-component real fuels, wide range of thermodynamic conditions, HyChem works as well as those surrogate model, if not better. Volcanic populace measure the flame speed at 1 bar and extinction strain rate in non-premixed counterflow. And we can see that model, this is a prediction. We did not tune the model parameter against any of this experiment. It does very well. If you're asking why it does so well, it's actually a foregone conclusion for reasons I already discussed earlier. It's a multi-component, so there's no reason to expect it won't work for flame speed. Okay. Folk can also measure high pressure flame speed in his spherical bump. The blue symbols with error bars are the measurements, and the red lines are HyChem model prediction. Okay. Without fitting, you see that the model works well under that condition. So the next question you're going to ask is, how much uncertainty do we have in the model? Or the other way to look at this is, how good is the measurement uncertainty for species profile, ethylene? In Wang's shock tube, Wang is always very proud that he has the most accurate measurement for species in a shock tube, and his measurement uncertainty is 20%. With 20% uncertainty, how does that uncertainty in the ethylene species measurement propagate through HyChem model parameter and into model prediction for global combustion property? This is what a symbol represents. Nothing on flame speed, somewhat on ignition delay time. But trust me, that kind of uncertainty is not that large as far as any of the reaction model is concerned. And then if you push me further, say how good it really is, your overall HyChem model. Well, actually, the current uncertainty of HyChem model can be pretty large, but that uncertainty is not in a HyChem lambda reaction part. That uncertainty is in a foundation field chemistry, that's C1 to C4 hydrocarbon part. Why is it? That's rate limiting. All the sensitivity goes to small hydrocarbon oxidation reactions or rate constants, not on the large species. Okay. All right, I'm coming pretty close to it. Thank you for bear with me. Some of you may ask, well, this seems to work only for high temperature combustion property, for diesel, and for some interesting combustion problems you have to worry about NTC. Without going into detail, HyChem can work with NTC with only measurements of CO and formaldehyde concentration. You don't need to have 10,000 reactions to describe that. You just need to have a few lambda reaction step. so long as you can identify the rate limiting step. Write it and just fit the parameter against that experiment. Can HyChem do NOx? Yeah, when we take a existing NOx mechanism from Peter Gladbach, published very recently, and slap it into the HyChem model, we can reproduce NOx concentration measured in our premixed flame. And those are the symbols here as a function of a cold gas velocity. This has to do with, I can plot equally the string rate, but since chemists don't understand what the string rate is, for the paper to be well reviewed, I just use cold gas velocity. But down below is really just a string rate, okay? And when the cold velocity gas increase, your string rate increase, the reaction time drop, therefore your NOx concentration drop. So the lines are HyChem prediction, symbols are experiment, and you have to agree with me. Without tuning any parameter, it works well. Now, just to summarize now, we have quite many HyChem models from jet fuel, rocket fuel, JP10, and the GEVO aviation, bioaviation fuel. We have some blends of bioaviation fuel with conventional jet fuels. We have gasoline. Those are E15 gasoline. And we have some other fuels. All the models are available for high temperature, skeletal. This is Professor Tianfeng Lu helped us to reduce those models to skeleton. Also have reduced the model at a reduced model level for all of these fields. Each of them have about 30 species, and they are very predictive for a wide range of problems for what we know. We have certain models that has NTC module, okay, and also NOx module. All right, so feel free to use them and let us know if you bump into any problems. And this is a list of HyChem papers. Don't have to read into details unless you're interested in assumption. And I would very love to see, the way how we do research is about by challenging existing notion of what can be done, what cannot be done, what is right, what is not right. So the only reason I list this list paper is if any of you wanted to know it more and challenge the model and therefore understand the limitation of this approach, feel free to do that. Just summarizing, many people have used this model now for gas turbine simulation, for rotating detonation engine, for hypersonics, and I have not listed any gasoline work, but those are essentially mostly internal work within Shell. Summarize, I guess for this audience, I hope I convinced you that you do not have to go to this large detailed reaction models and worry about how to reduce them. And for real fields, to worry too much about this 5-6 different components. Take HyChem, it works. The true advantage is you can reduce this model down to about 30 species. And that to many of you is a great advantage. And of course, some of you will tell me for your CFD simulation, 30 species is still too many. And that as a chemist, as a physical chemist, in fact, I'm sorry, I have to apologize here that this is the best I can do for you. You want anything to be better, you have to rely on people like Professor Chen Zheng and others who know how to deal with numerical efficiency, further reduction. These are the people who know this problem a lot more than I do. So all that said, I think I'm done, okay? And I just take a disclaimer here. What I told you actually now, what I'm going to tell you is a minority point of view. A majority of people working in reaction chemistry don't like what I tell you, okay? Simplicity is not shared as a viewpoint, is not shared by most of my colleagues. So take what I say at your own risk. All right, that's all what I have for. Thank you for your patience and apologies for going longer than I should. Thank you.
Thank you very much, Professor Wang, for your wonderful talk. So in the following, we will have a Q&A session. Okay. Mm-hmm. So let us check if there is any questions from the panelists. So panelists, you can unmute yourself and discuss with Professor Wang. We already have questions from Professor Zheng Chen and Professor Zhi Chen. So Prof. Chen, you may want to ask first.
Okay. Okay. Professor, thank you for the nice talk. So according to my understanding that HyChem is based on the assumption of time-scale separation that pyrolysis is much faster than oxidation.
Correct.
So I'm wondering whether there are some situations that this time-scale separation doesn't work.
Okay.
Firstly, I'm interested in detonation. You also work on detonation. In the detonation, the temperature and pressure after shock is pretty high. So I'm wondering whether the oxidation is still slow compared to the pyrolysis.
Right. What I did not discuss is that when time scale is not clearly separated, the reaction process is still that of a field pyrolysis first. And when you oxidize, you only oxidize the fragments. And that the reason for that is time scale again. If you start from n-dotted king, okay, and you generate an n-dotted king radical called n-dotted cell. There are 6 positions you can put this radical. If you look at the lifetime of this radical at a 1200 Kelvin, it's a few microseconds. Now you go to detonation condition. Behind the shock, if you get something of 2000 Kelvin, the lifetime drops to about 10 nanoseconds. Oxidation will still take longer regardless, okay, because of nature of this problem. So even when you see situation in which you do not see significant separation from species lifetime point of view, they will still be chemically isolated, even though not time isolated. Okay, so those are the things. Perhaps that's a great question, and we will have a couple of subsequent papers to look at this problem not from spatial point of view, not from a spatial separation, time separation point of view, but from chemistry point of view, explain why, even though you have time overlap, but the reaction mechanism don't change. They are still separated.
Okay.
And then if you push me further to say, well, if I go to 5000 Kelvin, if I expose this field to 5000 Kelvin, if you can do so immediately through a shock, okay, the only way you can heat a field, hydrocarbon field to 5000 Kelvin over time scales shorter than chemical time scale is shock heating, correct? And if you go to that high temperature, why do you even care if it's a 1 microsecond or 100 nanosecond or 1 picosecond? They are driven and controlled by gas dynamics, so chemistry don't matter anymore.
I see.
Yeah.
Follow the first question on detonation. We also interested in detonation, deflagration transition to detonation, DDT. In that process, the most important thing is the ignition delay time and also the excitation time. The excitation time is basically the duration of the heat release. In most of your results, you only show the laminar flame speed and the ignition delay time and also extinction flame rate. Do you look at the excitation time?
What time is it again?
Excitation time, the duration for the heat release.
Oh, yeah. Oh, I see. Okay. So it's a great question, actually. This is one of the things that we have been thinking about how to even do it. Okay. So if you look at the CND calculation, right, you have the induction length, then you have the exothermic length. Okay. Unfortunately, there are no known experiments we can use because the non-existence of 1D detonation. So while we can calculate the ZND induction length and we can calculate the exothermic length, we don't have anything to compare. 2 years ago, I thought that the one key characteristic we can compare it to is cell dimension in the detonation. But then we realized that those cell size are not fundamental property of the mixture. They're subject to boundary condition because of shock refraction in any practical experiment. So in other words, we're stuck. We know this is a problem. you raise a very good point. But right now, I do not know how to even provide, say, ask what experiments we have to do in order to compare to model prediction to tell us whether that excitation time can be validated or tested.
Okay.
And this is the thing that, as far as detonation combustion chemistry is concerned, we are scratching our head this moment.
Okay.
Okay. So the answer is I do not know. It's a
Okay.
it's a tough problem.
Okay. The last question is, on the other hand, that there is a situation maybe the pyrolysis process is very slow. Do you think?
We have not, we did a fairly wide range of ZND calculation because ZND is not the real detonation. This is exactly what I was worried about. Right now, HyChem model is being used in detonation engine design. I was very much worried about this initial period of insolubility. It's endothermic.
Okay.
Could it attenuate shock wave? In other words, shock passes, and you're going to have to, the endothermic process cools it. Now, funny enough, we have not found a condition for which you're going to see overlap, or initial pyrolysis is always very, very fast.
Okay.
If you look at any, let me just go back, maybe look at the numbers, it will be far more straightforward. The time scale is so interesting and unique that you really get into this problem, okay? Now, let's look at this one, right? You look at 1400 Kelvin 1 bar. Of course, this is not a ZND, but it's still shock heated, okay? And typically for a detonation problem, this condition, pressure is a little lower than a post-shock von Neumann temperature, right? Von Neumann condition. The temperature is about the same. Look at the time scale, right? It's about 100 microseconds. So this is very long, okay? This is very long. But you have to remember that in the detonation wave, the pressure is much higher. Okay, yeah. If you increase the pressure by a factor of 10, I can assure you this thing goes down within roughly about a microsecond time scale. Very fast. Okay. So to answer your question, my speculation is it's probably okay. How do I know that? Speculation. Do I know how to validate that part of chemistry for detonation application? I do not know. Okay, and in fact, we have a project specifically to address your question. How do we do that? And that's the good news. The bad news is I still don't know how to do it. There's nothing in detonation experiment that I can use to anchor and validate my chemistry. So maybe you have some idea, and I'd really like to discuss with you about how to do it. Okay.
Thank you.
Yeah. I think there are several other questions through the Q&A page.
Yes.
Also
yes.
through chat.
Yeah. So the next question is from Professor Zhichen, also from Peking University. So he cannot speak, so I will read on his behalf. So hi, Professor Wang, thank you for the talk. It is always a great joy to listen to you. And the question is regarding the RP3, which is the widely used jet fuel in China and some other regions. So do you have any plans working on HyChem models for RP3? This is the first question. And how different would they be from the Jet A and Jet P fuel models you have already developed? So these are the two questions from Zhi. Okay.
I see. Well, thank you for the question. As a matter of fact, we cannot work on RP3 because I can't find RP3 in the United States. Unless you can ship me some RP3, I'll do this for you. To answer your question, what we found was that in terms of global combustion properties, whether it's RP2, we test the 2 RP2, 3 Jet A, they are all more or less the same. So as a matter of fact, you can take any of the RP2 or jet fuel, you will not find them to be that different from your RP3. Okay. That's my speculation. But from our experience, you see this earlier. basic combustion properties, legacy properties, ignition delay, flame speeds. Among diesel fuel, gasoline fuel, and jet fuel, they are all same. Okay, so we actually, there's no fuel sensitivity. There's no composition sensitivity. It's this chart I showed you earlier. So now, among all of the fuels we tested, around tested, from jet, rocket, generic kerosene, diesel, and gasoline, they all fall on the same line. Okay. So are the expectation for the flame speed. If you throw another fuel on it, I'll be very surprised to see its ignition delay to be different.
Okay.
Or flame speeds to be different, unless it has a higher enthalpy of combustion.
Okay. Yeah. Okay. Thank you very much. The next question is from Prof. Wang from Beihang University. So, Boson, do you want to ask yourself to Prof. Wang?
Sorry, since I have network problem, I'm in a hotel.
I actually hear you very well.
Yeah, we
okay,
can.
okay. Okay, thank you, Professor Wang. It's very nice to listen to your talk. As a developer of finite rate turbulent combustion models, the reduction by HyChem is very friendly, I think. But since HyChem is based on the assumption of timescale separation, as Professor Chen Zheng mentioned, and the chemical timescale difference of pyrolysis and oxidation is over 20 times. Does it mean there are issues directly applying the HyChem mechanism to flamelate-like models?
Explain why you have a problem in the flamelate model.
Because the flamelate models is based on assumption the chemistry time is very fast, and but I saw this model, as I remember from your slide, this spans the chemistry time of the HyChem mechanism is spanned from 20 microsecond to 700 microsecond. And of course, if the 700 micron type steps is still much smaller than the flow time scales, it's okay. But I have not. Maybe I don't have much concept like to decide whether in a real combustion conditions or in engines like you mentioned in the gas turbines or rockets, in this kind of environment, is this a problem or not?
Oh, well, no, don't take this 700 microsecond and apply to gas turbine condition. Do you know why? This is diluted. Okay. This is 457 ppm of N dot K. Okay, it's 1/120th of the common fuel loading you find in gas turbine in which you have flames. This is our chemistry trick. We stretch the time by lowering the fuel concentration so that we can see details under relevant temperature. The time scale I show you here is not representative of the real flame condition you see anywhere. For real flames, the time scale will be much, much shorter because your fuel oxygen concentrations are much higher.
Okay.
Makes sense? The absolute time scale should not be important to you. Okay. What I'm talking about is a relative time scale.
Okay.
20 by 700 microsecond. In a type of gas turbine, let's say you go to 40 bar, you have a flame, you have a flamelet. Okay. That local convective time scale where reaction occurs is much, much shorter than I'm showing you here.
Okay. Thank you.
Okay, thank you very much. So we also have some questions from Q&A. The next one is from Professor Lu Yu. Okay, so his question is, he would like to know how stiff is the ODE systems resulting from HyChem? Yeah.
That's a good question. Now that question is actually, I can't answer very well. All what I can direct you to is, first of all, I have not heard that many complaints about the HyChem model being stiff.
Okay.
That said, stiff and not stiff is a relative word, a relative term. So in order to solve the stiffness problem, I suggest that you either talk to Professor Chen Zhen or talking to Professor Tianfeng Lu at UConn. These are the experts who know how to get rid, to a large extent, that stiffness. Applying numerical Jacobian and a variety of techniques of stiffness reducing approach. And I think Professor Zhang is also an expert in this. So from chemistry point of view, I always say that nature, as far as chemistry is concerned, should never be stiff. So if you do find a stiffness situation, that usually means something is not working right with the chemistry. Okay. So this is a top level opinions that I have. And if you do find in your code it's stiff, well, I'd be interested to know, to learn why this is so. Okay.
Okay, thank you very much. So the next one is from Jizhen Zhu. Okay, so hello, Professor Wang. I'm Jizhen Zhu from Shanghai Jiao Tong University. So thanks. If HyChem is used to mimic the NTC behavior, so how to determine the reaction rate constants, especially the low temperature reaction classes?
Yeah, well, this is something that I didn't have time to discuss, but 2 points, right? 2 points. First point is that Wang Hansen is continue to, and his students continue to work on this problem, and we work together on the HyChem. So what Wang is able to show is you need to measure formaldehyde concentration, and you need to measure CO concentration. With these two pieces of information, it is possible to back out the HyChem rate parameter and use for both extrapolation and interpolation. Okay. Second, if you ask me, are there any ways to get NTC chemistry right for real fuel? I can tell you HyChem, in fact, is the only way to do the right. Let me explain. When you get to NTC, your reaction time scales are no longer decoupled. Everything is meshed into one, and they're slow. That's why it's called NTC, correct? As a result of it, let's suppose the original assumption of the chemistry community is I'll study NTC behavior of heptane, then octane, then isooctane. And if I study sufficient number of them, I'll put them into, mix them together into a larger reaction model. Therefore, for a real fuel follow surrogate approach, you would examine a soup, a mixture of 5 components, and use these 5 components to predict NTC behavior. Logically, this approach would not work if you think about it. The chemistry is slow, they're not decoupled. So therefore, you should expect the NTC chemistry of fuel number 1, hydrocarbon number 1 in a mixture should interact with hydrocarbon of the second hydrocarbon, and so on and so forth. Therefore, in order to get NTC behavior predictable, you must understand a binary, ternary, and any combination of the fuel, right? If you do that, you never walk out of this problem. This problem will never solve itself. So my point is, if you want to do NTC, might as well do it directly on the fuel. Okay. So some ideas we have is we take, for example, cetane number, octane number, correlate this with the HyChem rate parameter. Then all you need to know is an octane number, the round and amount, and cetane number, and so on. You should be able to, those should be directly related to HyChem parameter. So this is the direction we're heading to. We're not done yet. All right, all what I have. But those are very good questions.
Okay, thank you very much. So the next question is also about NTC. Okay, at low temperatures, in the NTC range, is the fuel decomposition rate still very fast? Does the decomposition affect the overall reaction rate?
The very reason you start to step into NTC region where you no longer see fuel pyrolysis and fragment oxidation to be time scale separated is because the few fragments survive the temperature.
Okay.
And that's the reason they get oxidized by molecular oxygen. So when NTC start is for what I presented here, the high temperature chemistry assumption falls apart.
Okay.
In other words, the high temperature part that I discussed today roughly falls apart at around 1000 Kelvin.
Okay.
Okay, below it, you should expect NTC behavior to be important. Yet for NTC, again, you just have to look for a second separation of time scales. Time scale magically vary from 1 picosecond to 1 millisecond. Chemistry utilizes exponential dependency on the temperature through activation energy. And activation energy and exponential term are the best filter in nature. Bring out something that's important and suppress others.
Okay.
Okay. If the situation gets to a point that is so nonlinear, so complex, so not possible to have any scale to be separated, in other words, I have 100 reactions. Sometimes reaction 1 is rate limiting, sometimes reaction 10 is rate limiting. And if you have more than 10 reactions that can become rate limiting under range of condition, trust me, this field can never be used in a real engineering application. It's too complex, so diverse. For anything to work, if you're going to be able to engineer something, whether it's an engine or the fuel you burn, must be the rate limiting step. There are very few. If it's more than 2 or 3 or 4, it's a bad engine.
Okay.
I hope that those of you who understand the basic mathematics understand this particular statement I make. Okay.
Okay. Yeah. Okay. There is another question. Let me have from So Yang. So do you want to ask yourself to Prof. Wang?
Hey, so it's getting very late for you. Still up, huh?
No, it's okay. Actually, at your side it's 8:30, right?
No, here's 10:30.
Oh,
I'm 10:30. Yeah, 10:30.
Oh, okay.
Yeah.
Sure. Yeah. You have one question, right?
Yeah. Hi, Professor Wang. It's very nice to hear your talk. This I really have a new understanding of HyChem now, better than what I know before. So I have a practical question from one of my projects. So in our projects, we have a very special situation, which the field is continuously changed. And as you can imagine, we don't know the exact composition, but what we know is the theta number is continuously change, and we roughly know how it changed. So in the simulation, what we currently do is use the traditional surrogate model, and we just vary the combination of those surrogates to realize this theta number change. I'm wondering if we want to do the same for HyChem, how to do that, because you mentioned those HyChem parameters can be linked to the theta number. So I imagine there must be a way.
Yeah, well, here's the issue, right? So that's a good question. This must be a very unique combustor you're burning.
Yeah, very unique project. So I also cannot say details.
You probably, I understand. You probably use a field to do the control of something.
Yes. Yeah. It's a control project.
It's a control project. I understand that. So the controllability relies on the fact, for example, this I'm just using ignition delay time flame speed as an example. There might be extinction that impacts you, right? Okay. So I assume that when you do the control, you would put in not 2 practical fuels. You're not going to put in a jet fuel and a rocket fuel to do the control. You might
it's actually a jet fuel.
Gasoline, right? Like Ralph Rice's PCCI engine. It uses diesel and gasoline sort of to do the control. Fundamentally, that control, if it's only determined by high temperature chemistry, you would not be able to do much just because I expect those properties don't differ that much. So the control must be via NTC chemistry, which can be drastically different. Okay, so for that reason, you're right. It is possible when you get to NTC chemistry to focus on HyChem parameters that can be related to the CT number or to the octane number. That work is ongoing, and whether the system of equations can be closed mathematically, in other words, do you need more info or do we need more information than a CT and octane number to get to NTC chemistry? I cannot answer at this moment. My colleague Wang Hansen's point of view is all this, the amounts, the Wang, and in terms of octane number and CT number are simplistic. Those are engine-based properties that may or may not give you full information about NTC behavior. So Wang is actually pushing for more detailed shock tube-based test technique to determine the property. Might be CT plus some other properties. Okay, and if we have that, I'm confident, just from a mathematical point of view, we should be able to correlate those few related parameters to HyChem parameters. All right, but then if you are focusing this control for high temperature, due to high temperature chemistry, it's hard. The best control you're probably going to have is just inject the methane, inject the hydrogen. Those are a lot more, give you much larger variation. Okay, you see what I mean mathematically. So this has to do with this chart. In fact, the answer is in this chart. All right. If you do two component variation is very large, right? And you need a larger variation in order to give you the controllability. Okay, that means this strategy works the best for single component field, not for multi-component field, number one. And you need to limit this to very few components. All right. If you do go to multi-component mixture like a real jet fuel, doesn't matter how much you add and what is the second component you add, this is how much controllability for high temperature you have. So it won't be very sensitive. Okay, I might have offered too much information, irrelevant information, but I don't know if my answer helps.
Yeah, thanks, Professor Wang. Yeah, this is already very helpful. I think further about it. Thank you.
Okay, thank you. So because of time limitation, we will have one more question. Okay, yeah. So this question from a student from Tianjin University. So the first one is how to determine kinetic parameters of the 7 lambda reactions from the experiments, especially the H absorption reactions with different radicals. As I read the third HyChem paper of JP10, the kinetic parameters were first estimated from analogous reactions and then were tuned against experimental data by system optimization. Yeah.
Yeah, let me explain. That's a good question. Let me explain that. So first thing first, let me start from something simple, the lambdas. The lambdas by definition are the ratios of propene yield to ethylene yield. Okay. Yeah. And they're bound between 0 to 1. In general, thermodynamically, you're not going to find more propene than ethylene, for example. And this comes from flow reactor. So indeed, we do flow reactor experiments, and we take those ratio of propene to ethylene. Okay. And you get those lambda parameters right away. Now you have 2 parameters down. Okay. And 5 more parameters to go. All right. Then you take the benzene toluene ratio. You determine the third parameter as chi.
Okay.
Okay. So in other words, now you have 4 parameters left. And the 4 parameters left are related to here. Chi is known now. What's left is alpha and beta. Okay. Alpha and beta are related to radical time growth, therefore relate to overall global reactivity.
Okay.
Okay, these two parameters are now fitted in general against measured species profile, the time history
Okay.
for ethylene and methane.
Okay.
You have a couple more rate constants. And out of these 8 rate constants, only 2 really matters. Okay, so along with this species time history, you can, over a range of temperature through this temperature dependency, you can now pin the rate constants. The system is not as close as what I hope to see, but it's pretty close. Okay, and you can in fact show that the parameter space, when you plot it for the given set of data, is small. And this is discussed, in fact, in our the last paper we did, is precisely to address this question of how close your measurement can be with respect to the 7 + 8 HyChem parameters. And this is discussed in paper number 7. So if you're interested, you can take a look at what you find. As a matter of fact, what we showed is that in that paper, even if you do not have species concentration, okay, you have no shock tube measurement, you have no flow reactor measurement, you can guess the parameters to a point that your flame speed is only just varied by ±2 centimeters per second.
Okay.
Just through elemental conservation. It's good enough. Right.
Yeah. Okay. Thank you very much, Professor Wang, for your wonderful talk today. Okay. Thank you very much, and I encourage all the panelists to open your camera to thank our speaker today. Okay. Thank you, Prof. Wang.
Well, thank you so much for coming and joining us on the weekend. I know that there are no weekends in China, nevertheless. Thank you so much for joining the call, and I hope I'm useful to you as far as finding a small chemistry model for your work, hopefully.
Yeah, this is actually in high need, for combustion CFD modeling, actually. Yeah. Okay. Hope to see you soon. Yeah.
All right, I hope to see all of you soon, and I hope this pandemic is going to be over very, very soon, so we're going to meet each other in person again.
Yeah, in the conference.
I very much look forward to it.
Yeah, okay. Thank you very much.
Take care.
Thank you.
Bye-bye.
Yeah, thank you. Bye-bye. Have a great weekend.
You too.